Hello everyone, welcome to the main video of our micropaper. I am Hossein Golestani from the University of Michigan. In this video, I'm going to present HyperPlane, a scalable low-latency notification accelerator for software data planes. I've done this work with my colleague Amir Hosseini and our advisor, Professor Thomas Wenisch. Amir is unfortunately not able to do the presentation and attend the conference due to a medical reason. So let's get started. We are in the killer microsecond era, which is the time scale existing systems aren't good at. The killer microsecond issue is in part caused by high-speed peripherals and I/O devices such as solid-state drives, persistent memory, network cards, and PCIe-attached accelerators. They have microsecond scale access time, and due to their high throughput, they demand CPU attention every few microseconds. Moreover, online data-intensive applications leverage a distributed microservice-based software model that involves much finer-grained inter-server communication compared to a monolithic software architecture. At such low latencies, high throughputs, and microsecond scale service times, the performance of I/O software stacks is absolutely critical. The conventional approach for I/O communication, as shown in this figure, is using the OS kernel. Here, we refer to host applications and client applications or VMs as tenants. Kernel has several overheads such as context switches, system calls, interrupts, and cross-address space copies. To avoid these inefficiencies, a widely used approach particularly promoted by Intel Data Plane Development Kit or DPDK is to bypass the OS kernel as shown on the right. In this approach, the I/O software stack is implemented as a library OS as part of the user process. Although kernel overheads are avoided here, the downside of this approach is lack of centralization, as I/O devices in whole or in part are statically dedicated to tenants. To bring back a central view of all I/O devices and tenants, an alternative approach used by systems like Google Snap is a user-level data plane, as shown on the right. In the two kernel bypass software stacks shown here, I/O communication takes place through user-level queues. Moreover, for higher performance, cores need to spin poll on those queues to check for work or data items from I/O. Let's take a look at the operations of the user-level data plane, or equivalently, the software data plane. This figure shows the flow of data from I/O to tenants. The reverse flow from tenants to I/O is similar. A doorbell is associated with each queue on which a single or multiple data plane cores spin to check for data or work arrival. Here, data or work items arrive from an I/O device to a particular queue. The device rings the corresponding doorbell to notify the data plane. The data plane then dequeues the work, processes it, and transports it to the appropriate tenant. Finally, the tenant dequeues the items and works on them. An inherent issue here is that the number of queues that the data plane needs to watch is too much. There are several I/O devices and hundreds of tenants. Multiple queues are associated with each of them, so the total number of queues can add up to 1,000 or even more. The spin polling as a notification mechanism is not scalable to such a large number of queues. It also entails energy and resource inefficiencies and is not suitable for sharing queues across cores. In this work, we propose a notification accelerator for software data planes called HyperPlane. HyperPlane allows cores to not iterate over empty queues and halt execution when all queues are empty. It also enables multiple cores to efficiently monitor a set of shared queues. HyperPlane is composed of a familiar programming model centering around the queue wait instruction, which eliminates the need for spin polling. It is backed by a hardware subsystem, including a monitoring set and a ready set. The monitoring set watches for work arrival from I/O, and the ready set determines which ready queue should be serviced according to a service policy. Compared to a state-of-the-art spin pooling-based software data plane, HyperPlane significantly improves both throughput and latency. Here's the outline for the rest of this talk. First, I briefly describe issues of spin pooling. Then I will discuss design details of HyperPlane. And next, I will present evaluation results and conclude the talk. Spinning on a large number of queues, as shown in the simplified code snippet here, results in various inefficiencies. The traffic that passes through these queues is often unbalanced, and a large subset of queues are empty at any given point in time. Obviously, CPU cycles are wasted on checking empty queues. This results in lack of work proportionality, meaning that the amount of work that cores perform is not proportional to the work items in the queues. Also, at such a large number of queues, reading empty queue heads likely incurs cache misses, and this limits the scalability of spinning. Finally, multiple cores cannot efficiently spin on a number of shared queues due to coherence and synchronization costs. We have extensively characterized these issues in our previous paper on a real system, so if you are interested, please take a look at it. Our proposed design, HyperPlane as a notification accelerator, has the behavior as shown in the simplified code snippet here. The poll loop is replaced by queue-wait. Queue-wait either returns the ID of a ready queue or halts execution. The magic is done by HyperPlane's hardware subsystem, which includes a monitoring set and a ready set as shown in this figure. The monitoring set watches receive queues of I/O devices and transmit queues of tenants for work or data arrival. The ready set tracks ready queues and, based on a particular service policy for queues, returns a ready queue ID to a core that has called the queue-wait instruction. I'll describe the interactions of this subsystem with the queues and cores in the following slide. HyperPlane's hardware is first initialized. This includes initializing the monitoring set with the addresses of the doorbells of the queues to be monitored. The monitoring set watches for coherence write transactions to the doorbells, which indicate work arrival in them. When one of such write transactions is received, the corresponding queue ID is sent to the ready set. When a core calls queue-wait, the ready set chooses one of the ready queue IDs based on a specific service policy that I'll talk about more next, and returns the chosen queue ID to the core. The core first verifies if the queue is in fact ready using the queue-wait verify instruction. A false ready queue ID may be returned, for example, due to false sharing. Then the core dequeues the work item and calls the queue-wait reconsider instruction. Queue-wait reconsider either arms the monitoring set to watch that queue again if it is empty, or reactivates it in the ready set if any work item has arrived to it in the meantime. And finally, the data plane core processes the dequeued work item. Let's talk a bit more about HyperPlane's hardware subsystem. The monitoring set actually must perform key-value lookup operations, where the key is the tag of a doorbell address and the value is the queue ID. It is in fact a cache-like structure, and it has to be fully or highly associative to hold all the monitored doorbell tags. Our design choice for it is a cuckoo hash table, which has fast lookup time and a small conflict rate. I'm not going to talk about its details due to the time limitation, but if you have any questions about it, I'd be happy to go into detail in the live talk. The ready set in HyperPlane manages the order in which ready queues are serviced. The service policy may be round robin or priority based, in which each queue has a particular priority level. The ready set is implemented with a programmable priority arbiter, which is a widely used building block in on-chip networks and switching devices. Again, I defer the details to the live talk. We have modeled HyperPlane's hardware in Gem 5. Our software is inspired by and similar to DPDK, which is a popular software data plane infrastructure. Work items are sent and received through lock-free task queues. The tasks are, in fact, data plane transport tasks in the areas of networking and storage, including network packet encapsulation or encryption and erasure coding of data blocks. We have used the 16-core out-of-order processor where 1 to 4 cores are assigned to the data plane. I/O sources are emulated using generator cores. Our monitoring set and ready set have 1,024 entries each. The monitoring set is a two-way associative cuckoo hash table. And the programmable priority arbiter in the ready set has a Brent-Kong parallel prefix network design with logarithmic circuit delay complexity with respect to the number of entries. The overall area and power overhead of the monitoring and ready sets is less than 1% of the processor. Let's first compare the single-core performance of HyperPlane and the spin-pulling-based data plane at varying number of queues. As for the peak throughput, we consider a traffic which is concentrated in 100 queues regardless of the total number of queues. HyperPlane does not waste CPU cycles on empty queues and avoids corresponding cache misses, which are likely at large numbers of queues. As a result, throughput is not affected by increasing the number of empty queues in HyperPlane, but it constantly decreases in the spinning data plane from the left to the right of the chart. Now, let's consider the latency and see how fast HyperPlane or the spinning data plane finds a task in one of the queues and processes it. In the chart on the right side, the traffic is very light and there is minimal queuing delay. As we increase the total number of queues, the core in the spinning data plane has to check more empty queues and possibly incurs cache misses before finding work in the ready queue. But HyperPlane avoids additional latency of checking empty queues, and it quickly finds the work once it arrives, regardless of the total number of queues. So to sum up, we can see that HyperPlane achieves high performance even at very large queue counts because it does not check empty queues and avoids related cache misses. Let's move on to the MultiCore performance. Sharing queues across cores has important theoretical merits. First, as long as work exists in a shared queue and there is at least one free core, the core takes care of the work. This results in higher throughput in comparison to the case where the queue wasn't shared with that core. Second, lower latency is achieved because the probability of head-of-line blocking is smaller. We consider two configurations to evaluate sharing queues in a spin-pulling-based data plane. Scale-up, where queues are shared between cores, and a scale-out where no queue is shared. HyperPlane is inherently similar to a scale-up configuration because the ready set manages the ready queues, and it can assign any ready queue ID to any core. Let's take a look at some performance results for the case of balanced traffic, which is spread in all the queues. This chart shows the latency at varying loads. At lower loads, HyperPlane has better latency as it avoids checking empty queues. In the case of the spinning data plane with the scale-up configuration, both the latency at low loads and saturation throughput are severely affected because of the synchronization costs. HyperPlane doesn't suffer from such costs. All in all, as cores avoid synchronization overheads using HyperPlane, the potential benefits of shared queues are achieved. As for conclusion, we saw that spinning on a large number of queues entails several inefficiencies. Our solution for replacing spin pulling as a notification mechanism is HyperPlane, which avoids iterating over empty queues and halts when all queues are empty. It also allows multiple cores to efficiently monitor shared queues. HyperPlane's programming model is based on the queue wait instruction. It is realized with a hardware subsystem, including a monitoring set and a ready set. Thank you for watching this video. I would be very happy to discuss the details and answer your questions in the live talk. See you later.